Hello, Hubble Huggers, and welcome to another Hubble Hangout, to our latest humble Hubble Hangout, our hearty and happy Hubble. Okay, I'll stop.
Wow, the alliteration is strong in this one.
Well, it's easy with H's. It's easy to alliterate with H's. So anyway, so I guess of all the Hubble Hangouts I've done so far, I'm particularly excited about this one because the topic of this one is about something very near and dear to my heart. It is not an exaggeration to say that images from the Hubble Space Telescope have literally changed my life. And I don't mean that as a figure of speech. I could go on. That could be the subject of its own hangout, actually. But the images that the Hubble Space Telescope have taken have profoundly affected me. And so and have ultimately led me here with this great group of people that I'm about to introduce to you to talk about the Hubble Space Telescope and the images from it. So let me get started by introducing my co-hosts or cohorts or cohabitant. No, we don't live together, but with me is one of my co-hosts, Alberto Conti. Alberto.
Hi, Tony. How are you?
Welcome. Yes, he is the JWST innovation scientist. And Alberto, real quick, I know this is about Hubble, but I got to ask real quick, how are things going with JWST? We still on track?
Everything's still on track. We have a new instrument just delivered to Goddard a few days ago, and one is going into the cryo chamber for testing. So we're really doing well.
Awesome. So we're still launching in 2018 then. Nobody's dropped a primary or sneezed on the secondary or anything. Good.
Not yet. No.
Awesome.
We won't.
Okay.
Not because they wear masks, right?
Yeah, that's right. They have those sneeze guards and everything. Okay, cool. All right. Also with me is Scott Lewis from KnowTheCosmos.com. Hi, Scott.
Hey, Tony. How's it going?
Hey, Scotty. Hey, can I call you that? Can I call you Scotty?
You could for like once.
Oh, no, come on. No, I'm going to call you Scotty now. And then maybe in tomorrow's Hangout we'll give you a tagline, because for me it's like I stole Keep Looking Up from Jack Horkheimer, and of course Alberto's is Get Her Done. So we got to have one for you too.
Boy.
See, now we're going to have the YouTube commenters start calling me Scotty when I do Space
Scotty! Yes, you beam it. Okay. All right. Well, welcome, Scott. It's good to see you again.
Yeah, you too.
So let me talk a little bit about, before I introduce our other astronomers, I would like to get sort of to the point of what we're doing here. What are we doing and why? And we're kind of doing a social experiment this time around, where at the Institute we are compiling a list of the greatest images ever taken by the Hubble Space Telescope. And to do that, we want to get you involved and to get you help, your help. So to get our brains kind of kick-started into thinking about what images there are and what do we mean by the greatest images, let me introduce some of the people with me now. And we have, these guys to me are all rock stars. I mean, I have heard about them long before I ever met them, and I'm just really thrilled to have them with me on this Hangout today. Let me start with Carol. I'm just going to go from left to right. So with me is Dr. Carol Christian. Hi, Carol.
Hello. How are you?
Well, I'm good, thanks. And now you were famous long before I met you, because for many years you did the radio show on NPR Skywatch, and so I knew about you way before I met you. It's a pleasure to finally be in a hangout with you, though. So tell us a little bit about yourself. What do you do all day?
In addition to Skywatch, which we're looking to move to mobile media and the internet, I'm actually the Hubble Space Telescope outreach scientist, which actually to me is one of the best jobs in astronomy. It means that they pay me to read all of the research literature, which many astronomers, they have to carve out some time of their day to do that, but I get to do that as part of my job. So I get to see all the different research that's being done, and then I also support the news and the education products that are derived from those discoveries. So scientists are using the Hubble Space Telescope, making new discoveries, and then we roll that into news and education, and so I help do that. And it's like a great job. And the thing that's near and dear to my heart is citizen science. So that's the kind of science where we invite you to participate in our research by helping us find new galaxies, identify star clusters, maybe look for star formation bubbles in the Milky Way. All of those things are possible for you to participate in, and I'm pursuing some of those projects with my colleagues.
Oh, I know. Yeah, I know just how you feel about having the greatest job in the world. It's like sometimes I can't believe that I get paid to deal with the Hubble Space Telescope every single day. So I know just what you mean. I think we're going to be doing a hangout at some point in the future on some of those citizen science things too that you talked about.
I hope so. Yes.
Yeah. Okay. So crammed all together in one room, we have 3 astronomers who are extremely in my opinion, awesome guys. So with us, Dr. Frank Summers. Hi, Frank.
Hey, Tony. How's it going today?
Really good. So you are?
I am an outreach astrophysicist, outreach astronomer in the Office of Public Outreach here at Space Telescope Science Institute. So I also get to talk about the amazing things that Hubble does, working on the press releases, working on educational projects, giving teacher training talks, working with planetariums and museums, working on the website, doing all sorts of cool stuff. But as you know, my favorite thing to do is scientific visualization. I was the scientific visualization supervisor on IMAX Hubble 3D, and together with Zolt Levay, who you'll introduce in just a bit, we have a group here, the Visualization 3D team, that we take Hubble images, we visualize, we create three-dimensional models of them, fly cameras through them, and are able to explain the universe through 3D visualizations. That's what I like to do best.
Awesome. And then right next to him is Dr. Mario Livio. Hi, Mario.
Hi.
Go ahead.
Yeah, well, I'm an astrophysicist. I'm a theoretical astrophysicist, which means I hardly know from which side of the telescope one looks, but I look at what those astronomers are coming down with, and I'm trying to explain all of that and explain the universe. In my spare time, I write a blog called The Curious Mind, which hopefully everybody reads. And in my non-existent spare time, I try to write popular science books, the latest of which is called Brilliant Blunders, where I try to explain all kinds of complex scientific issues in a layperson's language to make science more accessible to a larger group of people. I've been with Hubble for many, many years, almost since launch, and I like every minute of it, and I'm sure I'll continue to like it, and hopefully also with the James Webb Space Telescope.
All right, awesome. Thank you, Mario. And I am also very pleased that Dr. Ken Sembach could be with us today. Ken is like the Hubble guy at the Institute. Ken, why don't you introduce yourself?
Hi, Tony. I'm the Hubble guy at the Institute.
Well, that was simple. Glad you could make it. Moving on.
This is the humble Hubble guy.
The humble Hubble guy, yeah.
Got it.
Yeah.
So Tony, my day job is to basically watch out over all things Hubble here. I'm the head of the Hubble Mission Office here at the Space Telescope. And I have the privilege of working with many, many wonderful people here and at the Goddard Space Flight Center every day to keep Hubble operating efficiently and producing all that great science it produces. I'm trained as an astronomer, so it's a particularly satisfying job.
Awesome. Thank you. And like I said, welcome. I'm really glad you're able to make it. And skipping over Scott and me, who we already have introduced ourselves, with me is Zolt Levay. He also is the Hubble Heritage Team Lead, and he's one of the guys that are sort of responsible for giving us some of the most beautiful images Hubble has ever created. Hi, Zolt. Welcome.
Hi, Tony. Hi, everybody. Yeah, what more can I say? I've had the privilege of putting together a lot of these Hubble pictures from the data. So we take the data out of the archive and put the images together and make them available to everybody.
So in some way we are really showing your work today, sort of, right?
A lot of my work and a lot of other people's work.
That's right.
So I work with a team. Tony talked about the Hubble Heritage Team. This is a group of folks here at the Institute who've been, for a number of years now, have been trying to find and publicize the visually best, the aesthetically best, if you will, images from Hubble. Not so much concentrate on the science aspect of it, but more the visual aspects of it. And I think that all goes into what we're going to talk about today a little bit.
Yep.
Yeah, so there you go, guys. There's our panel of astronomers and people working on the Hubble Space Telescope. I guess so. And we decided here at the Institute, like I mentioned at the top of this hangout, that we're putting together a list, a comprehensive list as best can be done. And because we operate the Hubble Space Telescope, and we've just given you our credentials, this list will be the official one. We are the governing body for the
And much too long one.
Yeah.
Oh, yeah.
And so because these images will be the greatest, they will be canonized as the greatest images. But first, we have to kind of talk about what we mean by that. What do we mean by greatest? I mean, I know why, for example, I'm greatest at, you know, whatever it is I do, but I don't know what we mean by great Hubble images. And I guess you could think of it in two ways. There are the greatest images that have produced the most scientifically useful data, or have made us look at the universe in a way we may have never done before. And then there's just the pretty pictures. There's the most beautiful Hubble images. Those are also great and have their own. So when we say greatest, we mean all of it combined, both because what may be scientifically quite amazing and great doesn't necessarily mean they're pretty. So we want to kind of talk about all of that together, and we are all, as a team, going to sit and discuss which ones mean the most to us. So as Mario mentioned, that the Hubble's been around since 1990. It has been around a really, really long time. And I guess the first thing I'd like to ask you guys is, why is that? Why is Hubble one of the ones that, of all the space telescopes, it's still around, it's still kicking, it's still alive and well and doing great things? Who wants to try?
Well, any one of us could try to answer that.
Go for it.
Well, Hubble was built as, from the beginning, Hubble was built as a serviceable telescope, which meant that shuttle astronauts could get to Hubble. Hubble is in a low Earth orbit. They could grapple Hubble, and they could take out old instruments and put in new ones. They could also repair old instruments and so on. So in some sense, you know, because Hubble was serviced 5 times, it was actually at every such time that it was serviced by the shuttle, it was made almost into a new telescope, in the sense that it had new instruments on board, things that needed repairs were made, and so on. So this gave it its enormous longevity, but not only just longevity, but also productivity, because it, you know, essentially renewed itself with every servicing mission.
Right, and like Spitzer, you know, had enough cryogen to last for, what, 5 or 6 years, and then it had to go into its warm mission, right? And we were able to go and replace the batteries and replace gyroscopes, and you know, all of the consumables on Hubble were able to be replaced, and that allowed it to be so long.
Yeah, that was part of the, I mean, part of it is the logistics associated with just making Hubble a new telescope, but the telescope has staying power in that it has public appeal, and it has public appeal right from the start. Right?
And why do you think that is, Ken? Why do you think the public appeal is so strong for this telescope?
Well, I think early on, when Hubble had some initial problems with the mirror configuration, and the astronauts were able to go up and repair it, there was a great human interaction with the telescope that resonates with people.
Drama, really.
There was
drama.
Yeah, real drama, exactly. And the fact that when the astronauts repaired the vision on Hubble, that the telescope was able to produce such sensational pictures, it gave the public an immediate visual representation of what was possible with this telescope that they hadn't seen before. And I think that was just the start of what's been, you know, 20-plus year history.
Yeah, I think
I saw images.
Yeah, in that sense, do you think, Ken, so it really did open a new era for astronomy?
Oh, absolutely, in many ways.
Right.
Yeah,
and the thing
oh,
that's
go
happened
ahead.
with some of the imagery is that the imagery has public appeal. We make sure that the imagery gets out there, and all of the data and all the discoveries. And in fact, when we started putting these images out more than 20 years ago, all of a sudden we started seeing other sciences doing the same thing. I mean, they were like trying to find the coolest images of biological organisms and medical imaging and all that. And so it's really sort of changed the way that scientists present their science, and in astronomy we have the beautiful cosmos to bring to the public.
Yeah, and I know what you mean about the drama part of the repair part, because I remember back in my former life when I was in the solar physics, the Solar Maximum mission was one of the first, if not the first, telescope to get repaired by a shuttle, and that opened up a lot of interest in solar astronomy, whereas before there wasn't before. So I know from personal experience, the scientific images that have come off of Hubble have been what has affected me the most. The beautiful, aesthetically pleasing ones were certainly great, but it was the scientific. In fact, if you look at the deep field, which is the one that first caught my attention, that's not a particularly pretty picture. It's just a bunch of fuzzy dots everywhere. But it was how it was taken that really captured my imagination. What do you guys think is well, I'm asking a bunch of astronomers this. Which one do you think is more important, the science or the aesthetics? But let's go ahead and do it. Which one do you think has a bigger impact on the public?
Well, I think the aesthetics has a bigger impact on the public, but I think that the fact that every now and then you come up with a really big discovery, and plus that with Hubble, as Carol described, we have managed actually to take the excitement of discovery and bring it into the homes of people all across the globe. That has made the scientific part also important for the general public. But there is no question that much of the popularity of Hubble derives from those just astounding images.
Right, and I would take that a little further, because the beauty allows you to go in and present the science. When I do the teacher training talks, and I talk to all of them, the images get the attention, and they want to know more. And that is such an easy way to segue into, okay, now here's what it really means. Here's the science behind it. Here's that amazing astronomy that we discovered using this image. And so it's a combination that really gives it, the fact that there's truth behind the beauty makes it that much more powerful.
And Tony, I'll say that a little bit in defense of your favorite image, which isn't necessarily my favorite image, but for the Hubble Deep Field, the original Hubble Deep Field, we made this big display of it, and we had it out in the public, and we could see people walk up to it, a few people together, and they would start classifying the galaxies, and then sometimes, an astronomer would go over and say, "Do you know what you're doing? You're doing science." What? I'm doing science? But
oh my God! Stop that!
Yeah, really, it was a very engaging way of, as Frank says, of those images make people start to ask questions about what is it? Why does it look like this?
Yeah. With the deep field, it's. Go ahead, Albert.
No, go ahead, Ken. I think I'm going to say exactly what you're going to say.
With the deep field, that's a really interesting case, because, as Tony was saying, it may not be the most visually striking image when you just look at it in sort of a cursory fashion, but when you show people it and you start to explain to them what it is that they're seeing, it starts them thinking about what it means.
Exactly.
And then suddenly the beauty of that image is apparent. That whereas just from a visual standpoint, an immediate visual impact, it might not have been before. And I think Carol was basically getting to the same thing.
Yeah.
When people start talking about what's in it and doing something with the image, it becomes a lot more interesting.
When you say that in that image, every point of light essentially that you see there is a galaxy with 100 billion stars like the sun, this literally staggers people, and it also gives them a strong sense of our place in the cosmos.
I was actually going to say exactly that, because I think it's was an eye opener in so many ways, and perhaps I find it extremely beautiful, but I guess I'm biased. But I suppose that it's also it puts something into perspective, as Mario said, because when you sort of look at this completely blank patch of the sky where we pointed our telescope and we see 10,000 galaxies or 3,000 galaxies in the case of the Hubble Deep Field, for example, and then as Mario said, you point out that every little dot there is a galaxy that is either forming or it's similar to our own. That's quite mind-boggling, and it does have a very, very different feel to, for us humans. It sort of puts it in a different perspective, and it's quite. I remember, when it came out, I was a graduate student. It was quite dramatic, and people wanted to know more. And he has told us so much more about just galaxies in general, and it's a fascinating image.
Oh, I know, and I mean, I've seen it plenty of times before, but it wasn't until I learned how it was taken and the context of that image that I couldn't stop thinking about it. It absolutely blew me away. It was like, we stared at this blank spot in the sky for all this time, for hours and hours, and built up this image that was filled with galaxies in it. So let me ask you this: these images, this image in particular, I think was taken using Hubble's. There's this thing called director's discretionary time or something like that, right? That's where you can just sort of decide how to take a picture.
Correct. Correct.
Was anybody worried about how that would turn out? Was anybody worried? Was it a risk to take this image, point the telescope, a very valuable piece of hardware, at nothing?
Yeah, there were many prominent astronomers saying that was going to be a waste of time,
Wow.
Scientifically, and the results speak for themselves. It's one of the most productive projects that Hubble's ever undertaken in terms of the number of scientific papers and citations and so on that have come out.
And we've repeated it several times with the ultra deep field in the 2009,
Right.
2010.
No, it was a very controversial.
I want to remind everybody also that the area of the sky you are looking at here is just about something like what you would see if you looked through a drinking straw. Yeah. So, I mean, that gives you another impression of what it is you're seeing.
There's very tiny patch.
Exactly. Well, there's more than 10 million patches on the whole night sky of this size. So the whole night sky, you'd have to tile this over 10 million times to cover the whole night sky.
And if you do the math, you see that in the observable universe there should be something like 200 billion galaxies.
Do we all feel small enough now?
We all feel small enough.
Have a nice day. Okay, now we're going to come back to this image in just a bit, but it occurred to me that I have been neglectful in not telling people how they can participate. So we're building this list, but we want you to help us build it. And the way we want you to help us build it is to comment. Tell us which ones you think are Hubble's greatest images. But don't just post a link on the comment thing of this event page or anything. Put some effort in it. Tell us why it's important. Why is that image great? And because we're going to all take a look at this and build the list based on your input. So the way you can let us know is you could comment on this event page if you want to. You can go to our Facebook page, facebook.com/Hubble Telescope, and interact with us there. You can tweet using the hashtag that you see here on my lower third called Hubble Top Shots. You can also use that on the G+ page as well. Also, we have a Hubble Space Telescope community. The link to that community is on the event page of this on G+. I would encourage you to join that community. Make your posts there. Discuss other people's pictures. Plus one it. Tell them why you think it's a good idea or a bad idea that image be included. But interact with us. Let us know what you think, because this is it. Like I said, this is going to be the list. And if you want to be a part of it, you're going to have to prove it to us that this is in fact a great image from Hubble. So there, I wanted to.
So if you're with us on Google Plus as well on the event page, if there's something that you found from the Hubble site gallery, take the image itself and put it into the event page. So you're not only sharing which image, the title of it, but you can actually show the world exactly what you're talking about and why is that important to you.
Yeah. So we want your input, and we want you to tell us what the greatest images are. So let's get to some specifics. Who wants to give us their favorite image? Who wants to go first?
Oh, Tony, nobody's speaking up. I'll do it.
Okay, go ahead, Ken.
Go, Ken.
I like Abel 370.
And that's a picture, and why do you like that?
This picture I like for several reasons. The first reason is that it was one of the first things that we looked at with the advanced camera for surveys after it was repaired during servicing Mission 4. So it has kind of a personal investment in it that a lot of the people have here that we have a lot of pride in. But scientifically I like it very much because it shows the effects of gravitational lensing. That is the universe itself acting as a lens on the light that's coming from very far away. And in particular, you don't need to be a scientist to appreciate what's going on in this image. You can look at it and know just from looking at it that, in fact, matter warps space enough to distort light. And you can see that in these arcs and various trails that you see around this image. The light from distant galaxies gets warped or transmitted through this lens, this gravitational lens of this foreground cluster, and you end up with these arcs. The big arc on the right is particularly striking. Again, there you can see that not only is that cluster in the center of the image warping the light and pulling that light of a distant galaxy into the background of the background galaxy into that magnificent arc on the right-hand side, but if you look along that arc, you see that each time that arc light passes one of the nearer galaxies, the galaxies themselves warp that light. So Einstein was right. You can tell that just by looking at this picture without having to know really any of the physics that's going on. I think it's just an incredible picture.
Agreed. And so just to clarify, this is a cluster of galaxies, and each one of these dots and smears is a galaxy in here. But every once in a while, what you'll see are these kind of long, stretched out looking stretchy things, and those are individual galaxies whose light has been warped by the gravity of these other galaxies around it. Now this one really dramatic arc on the right, that one is the one that is being stretched out. Is it by this elliptical galaxy here, or in the right next to it there, or is it some unseen material somewhere?
There are two concentrations of gas in this of matter in this image. One is right on the center of the image, and that's the main one that's stretching out that light of that arc. And you can actually see the galaxy within that arc repeated multiple times at both the head and the tail of that arc, for example. And then, as I was saying earlier, there's also a shape induced on that arc by the individual galaxies that are near to that arc on the sky. And you can see the light, the arc kind of bends around each of those galaxies there.
Let me only clarify, Tony, that galaxy, that the light of which you're seeing as being stretched like this, that galaxy is actually much farther than the cluster of galaxies that you see. So what happens is that the cluster of galaxies acts like a lens between us and the more distant galaxy, and by warping its light, it causes all these shapes that you see and the stretching of the light.
I remember the first time I saw that, it was amazing. Go ahead, Frank.
Well, I was going to say, I like to call this visual proof of general relativity.
Yeah.
Because, I mean, when you learn general relativity in graduate school, it's the Christoffel symbols and all these Riemann tensors and everything. It's all this complicated mathematics. But you just have to look at this image from Hubble, and you can see the effects of general relativity in it.
Is Hubble the first telescope to ever get this? I'll get to you just a sec, Carol. Sorry. Is the Hubble the first one to be able to take an image of gravitational lensing like this?
No.
No.
Okay. But there have been telescopes on the ground that have certainly done this, but none to the type of resolution or the depth of field that Hubble has been able to do.
Got it. Sorry I interrupted, Carol. Go ahead.
That's okay. We have many beautiful examples. One of my favorites is Abell 2218, but I wanted to bring up a teaser, an appetizer, because an appetizer is that in the fall and over the next several years, we have a group that is working on 6 lensing clusters, and the project is called Frontiers Fields. And the idea is to look at these 6 clusters, and then there will be theoretical models to understand in detail what the mass distribution of the cluster is, and also information about the more distant galaxies which are being lensed. And so there'll be 6 examples, and people are already working on those even before the Hubble observations are being taken. And another really interesting thing is that other observatories are already planning and starting observations of the same cluster. So we're going to have all kinds of information: X-ray, infrared, Hubble, ground-based observations of these 6 clusters that will be coming out over the next couple of years. And so you should stay tuned, and you might be able to participate in trying to find some of those little lens pieces when we get those observations. Sorry, and someone's calling me about that right now.
That's right.
They want to know more.
Frontier Field, sign me up.
Let me just mention that these are observations indeed for the coming future, but there already are observations. There is a program called CLASH, which looked at 25 such clusters and produced already some incredible results, including lensing and many other results. And those results are coming out right now as we speak.
Okay, acronym test. I have to remind me of it. CLASH, cluster, lensing, and
supernova search with Hubble.
Exactly. Supernova search. Yeah.
Thank you, Frank wins. Frank wins. Okay.
No, I only because Ken checked me on it.
Oh, okay.
Another advertise. This is another teaser. Is that these lensed objects, and this is advertisement for the JWST scientist here among the group, is that in some cases, some of these little galaxies that are being lensed, if the massive cluster in the front wasn't there, we couldn't actually see it. So this is a clue of what we're going to see with the James Webb Telescope in the future, because the James Webb Telescope is much bigger, and it will see these galaxies directly. So this is Hubble's little lens preview of what's to come over the next.
Yeah, I'm glad you brought that up, because that's an important part of the Frontier Fields thing. I think is using gravity as lenses to make Hubble more powerful than it would otherwise be, and so it can see a little bit further back and get galaxies it wouldn't see without the help of gravitational lensing. And I think, in fact, I've been trying to get Jennifer involved in this too. I think we're going to have a hangout on this pretty soon. Alberto, we're going to have to get that going. So okay, let's talk about some more images. Zolt, let me get you in on this. You've been awful quiet.
You want me to go in a different direction here?
Yes, please go.
Yeah,
okay. I'll go in a more aesthetic direction.
Okay.
Yes.
Let me turn on my screen and let's see here. Start screen share.
Okay, I have you embiggened, so go ahead.
Okay.
There you go.
So I'm going to talk about this Carina Nebula image. Can you all see it?
Yep.
Sure can.
This is one of my favorites. It's hard to pick a favorite, obviously. There's so many. But this is actually one of the largest in terms of resolution, in terms of number of pixels, one of the largest images that we've made from Hubble.
What is the resolution?
The pixel size is 32,000 by 16,000, roughly. So it's about 500 million pixels.
So this is a mosaic then, right? This is the Hubble camera is not this big, so.
This is 16 separate frames stitched together. There's another odd thing about this image. Well, maybe it's not odd, but another unusual thing about this image is this is a combination of Hubble data and ground-based data. So the Hubble ACS camera took images in the light of hydrogen, so it's H-alpha, and but that's all that Hubble had for this large mosaic. But we were able to take an image from a ground-based telescope, from a Ceratololo, which took an image of a much wider field image, and but that was taken in 3 different filters, in the light of hydrogen, sulfur, and oxygen. And from that image, we were able to make a color composite. And so we took the color information from the ground-based image, but we're able to combine that with the black and white image from Hubble, which has much higher resolution. But we're able to preserve all the resolution from the Hubble data, but layer in the color from the ground-based data.
Wow.
So if you zoom into this image, I mean, this is showing a much reduced resolution. If you zoom into this image, you just see it's extraordinary. You see these little tiny knots where there's the gas and dust are condensing and new stars are being formed. There's just stars being formed all over this region of the Carina Nebula. And yeah.
How many sub-images did we use as pictures, individual picture releases from this image? Because I can count at least 3 or 4 of them, right?
Well, we had several cutouts that we released at this time, and then the other thing we did was there's a remarkable spot on this image. In this particular place, it's kind of in the upper or middle right portion of the image. You see this kind of funny-looking thing that looks kind of like a mountain on its side. And we were able later to take another image with the new camera, with C3, and all do 3 filters with Hubble. So we made a color image from all Hubble data. This is the image that we released for Hubble's 20th anniversary 3 years ago.
And which we call Mystic Mountain.
Mystic Mountain, yes.
That's your name, right, Mario? You gave it that. You christened it, right?
Yeah, I gave that name.
And we.
Oh, I thought we were supposed to start calling Mario Mystic Mountain.
Mystic something, maybe.
No, that's Matt's nickname.
Okay, so in addition to being amazingly beautiful, there is...
Can we see that image, by the way?
Yeah, I'm
Mystic
pulling it up.
Mountain, yes. Actually, this is in, let me...
No, that's not it.
2010 13A.
Wait a minute, just hang on. Here it is.
Oh, there's another one, too.
There, yes.
Yes.
That's it.
Oh, there you go. Yeah.
Put it back.
Which one?
No, I have it on my screen. You should be able to see it.
Yeah, we see it.
Yes.
Okay.
I have it. I have it, and you're big.
Yeah.
So.
I have the old one either.
So this this is actually a wider view than we initially released, but it really shows well the at the very tip of the tallest pillar. You see jets coming out on either side, and that's a telltale signature of a new star being formed down in there. So.
So what are those? What are those flares? That's not that's an actual feature. That's not an optical artifact or anything. It's a real.
That's a real feature.
Yeah.
Optical artifact.
Well, you know how on these stars you see these spikes here? That's not.
No, those are
the
jets.
entire thing's a smudge.
Those are jets coming from when a new star is being born. There is like a disk formed around it. And from the center of that disk, there are jets that emanate to both sides, and those are the jets that you see.
The birth announcement of his newborn star.
Yeah, it's like a.
So tell us a little bit about the camera that took this. This was taken with the WIF C3, is that right, or?
Yeah, Ken maybe wants to talk about that.
Yeah, so that was the new infrared camera, infrared and optical UV camera, panchromatic camera that was installed during the servicing mission in May of 2009.
So what's so great about that? Why do we want images in the infrared? Why is that important?
Well, it allows you to see through a lot of the dust that often obscures the ultraviolet and the optical regions in some of these images, and so you can actually look into star-forming regions like this. In some cases, you can actually look right through them and see astronomical phenomena that you wouldn't have been able to see otherwise. There are some really good examples in the Hubble site gallery where you can blink the optical and the infrared images together. I don't know if we can pull any of those up.
Yeah, I've seen those. Those are really great. They kind of fade from the visual to the optical to the near infrared, and those are.
Well, I can show one of the infrared images. Let me show the horsehead image.
Yeah,
yes,
show that.
I was hoping you would do that because the horsehead is like stunning. It's one of my favorites.
Now this just came out.
Yes.
Well, this we did a few months ago, and again an anniversary commemoration to commemorate the 23rd anniversary. So the horsehead, of course, is this object that every astronomer likes looking at. So we decided to do it in the infrared, and this was maybe not as big a gamble as the Hubble Deep Field was, but it was a little bit of a gamble because we didn't quite know what we would be getting. But we did want to exercise the infrared camera a little bit, and so we took two filters with the infrared camera, and this is a color composite of those two filters, and it's, to me, really remarkable because we're seeing the horsehead itself almost in a negative view from what you see in the visible. So what's bright here largely is dark in the visible. And in addition to that, we're seeing into the nebula, but we're also seeing behind the nebula, whereas in the visible light at the top of the image, it's very bright, and we're not seeing anything behind it. But here, that material becomes completely transparent, and we're able to see stars and even very distant galaxies much farther away, right straight through this nebula. And so it's really remarkable.
Yeah, Zolt,
So Zolt is telling a very benign story here, but Mario and I can attest that we had many discussions about taking this data, many arguments about exactly what filters we were going to use. Oh, we're not going to see anything, blah, blah, blah. And when the image came out, we were all just stunned.
We were blown away.
Like, oh my goodness.
Yeah.
Let me just add something, Tony, because you asked why do we want an infrared camera at all. So, of course, another big reason is that because the universe is expanding, light from very distant objects.
I was hoping somebody would say that.
Light from very distant galaxies is actually redshifted. It is shifted towards the red, and if you go even farther into the infrared. So if you want to study the very distant universe, the way to go is the infrared, and that's the reason why the James Webb Space Telescope, it will actually look exclusively in the infrared.
That's right. I always say the future of astronomy is in the infrared.
Yes, it is.
It's pretty hot.
Yeah. I was actually showing some work that Frank did actually from the Horsehead Nebula, where you can actually, since we have a little more information than just two-dimensional image, we can actually do a 3D. Maybe Frank, you want to talk about the 3D Horsehead Nebula tour?
Yeah, this is a visualization that Zolt and I and our team and Greg and Lisa did. Just a very simple camera move to show you the three-dimensionality of the nebula, because what really makes it real cool is that if you do a crossfade from the visible to the infrared, you're playing the ESA version, not the Hubble site version.
Correct.
All right. What the Hubble site version has the cool crossfade from the visible light to the infrared light. You just see how much more we see with the infrared, and it becomes visually obvious why we really want to use both wavelengths.
Yeah. Let me see if I can try to find that.
That's amazing work, Frank. I love that that fly through. It's really good.
Tony, when that image came out, one of the engineers here changed the way that I look at that nebula forever. And he said, I asked him, what did he think of the image? And he said, I never realized there were so many galaxies behind. And actually, if you go, again, if you go to Hubble site and you look at it up at the real nice resolution that you can get there are just hundreds of galaxies behind this thing. It's amazing.
That's another point we should emphasize, that when you go to Hubble site, you get every pixel that we as the astronomers see.
Yeah.
So you want to look at that image in all its glory, you get every single pixel we see, so you can see all those galaxies that we look at.
I mean, the Horsehead's 20 degrees off the galactic plane, so it's up out of the dust, most of the dust of the disk, and then with the infrared camera, you can see right through the dust of this region to those background galaxies, as you noted before.
Okay, before we leave this image, I just want to ask you guys a question that I was wondering about. What is the effect? I mean, right next to the Horsehead is a really bright star. I believe it's Zeta Orionis. Is that right? Really, what effect do really bright stars have on Hubble?
Are you talking about Sigma Orionis, the one that's actually?
It could be. Yeah, the one that's right next to it. The one, there's a really bright star that when I was looking. That is, one needs to, it's within a field of view of a small telescope. But I was just wondering, when you're getting close to bright stars or objects that are close to very bright stars like that, is it a danger to Hubble? I mean, do we have to take any precautions?
You mean when we point near? The telescope is not getting near a bright star. We're pointing near.
Pointing near. Thank you, Carol.
The telescope stays with us.
Yes.
It's not pulling a Comet Ison and grazing.
That'd be kind of cool, though. Come on.
Yeah.
Tony, the answer.
But it is pointing near.
Yes.
The answer to your question depends on what instrument we're using to look at the nebula or the star that's near the nebula. In some cases, it could pose a health and safety risk to the instrumentation by overlighting the detectors. In other cases, it might just end up saturating the detector, in which case, the worst thing that might happen is that the detector kind of blurs out in that particular image, but then recovers fully from the exposure afterwards.
Let me point out that there is one star that you definitely don't want to point the telescope to. That's the sun.
Oh, yeah. Now, we take lots of precautions are taken to avoid that, right, Ken?
Absolutely. We have a definite solar avoidance zone, and there are many safeguards in place on Hubble to make sure that we don't point at the sun, even as a last resort, closing the baffle on the front of the telescope.
Right.
Which you never want to do because you don't ever know if it's going to open again.
So why do we put? So is that what it's there for? Just as an ultimate safeguard against pointing at the sun? I mean, I've always wondered. It's always open, isn't it?
Well,
we don't ever close it.
No, we don't ever close it. The only time we ever close it is during servicing missions.
Right.
So when the telescope's put into the payload bay of the shuttle.
Okay.
And even then, we always worry, will it open again?
And even then, we don't release the telescope until we've opened it. Right? But you're right, Tony. It's kind of the ultimate safeguard. Although if it had gotten to the point where sunlight was actually near enough to be going down the baffle that we closed that door, we'd probably already have had problems. So in that sense, it's not terribly useful.
Right.
The other safeguards that are in place are far more useful.
Okay, we haven't gotten. We're running out of time. I see we only have about 15 minutes left, and we haven't talked with Frank and Mario about theirs. Frank, you got a favorite you'd like to share?
Actually, let me share. Go to the third image in mine and bring that up on screen share. I'm going to do something in praise of dots. Okay, because we show all these beautiful images.
Yeah.
No.
I like dots.
In praise of the dots of that Hubble sees, because this shows off Hubble's resolution. Okay, and pull that up full screen.
I think they're pulling it up for us.
Yeah. All right, go to the next slide, and the next slide. There we go. Okay.
Good job.
All right. Yeah. So this is the Pluto system. Okay, Pluto and Charon, and the 4 moons around them, Nix, Hydra, and then P4 and P5, which have been recently named Kerberos and Styx, and Hubble is the only telescope that can really see with such fine resolution to see these tiny little dots around Pluto way out at the edge of our solar system. And I like this image because it shows off the amazing resolution Hubble has, but what it also does is it shows that, we think we know our solar system. We think that there's nothing new in our own astronomical backyard. But here are, we've known about Pluto and Charon since 1986, but all 4 of those moons were discovered by Hubble in the last, what is it, since 2003?
Just a few.
2005, actually. So 8 years, within the last decade.
Within the last decade.
We've discovered these 4 new moons, and Hubble's resolution allows us to do that. And so our astronomical backyard really, we're learning new things with it. All right, and so let's skip that sort of a couple more because I want to. There's another red dot. Go, keep going, keep going.
That was red.
Keep going. The next one, okay. And so I want to take that one step further, and not planets around our own star, but I think one of the greatest things in our lifetime is the discovery of planets around other stars. I mean, this is the most compelling story we have to offer, that we are seeing other solar systems. And this image here, I know it looks like the Eye of Sauron from The Lord of the Rings, but what it is we're blocking out the light of this star called Fomalhaut. Okay, that's what's called the chronographic mass to block it out. And you see this dust ring around it. And because the shape of the dust ring was sort of pulled off center, we suspected there might be a planet. And over on the right, there's that small little box, and then the pullout that shows you Fomalhaut B. And the 2 images we got of it from 2004, 2006 to show it had a nice orbit around Fomalhaut, and really we're seeing a planet. Well, this is the first visible light image ever taken of a planet around another star. And so I brought up these 2 images to show you that, research science is generally done with these dots, okay? It's not, yes, we get some fantastic, beautiful images, but, some of the cutting edge, I've always thought I should give a talk in praise of red dots because, a lot of our cutting edge science is done by just looking at these dots, and the implication of these dots are just fantastic.
Yeah, that is an amazing photo or set of images, actually. So the Hubble came and visited it twice. Oh, what do you?
No,
what do you got
go
there?
ahead, Tony. Go
what
ahead.
do you got there?
Later. Go ahead.
Okay, so it visited this system twice, and it has a mask in front of it that it uses to block out the bright star. Is that what you said?
Yeah, that's what's labeled in the image. It's a chronographic mask, and so it's blocking out the light of Fomalhaut so we can see the faint things around it. Just like you would at sunset, you put your hand up to block the sun so you can see the road as you're driving down. Well, we're doing that same sort of thing.
So what's that ring there? What's it about?
Well, this is a ring of dust around the star formula. We have dust rings around a lot of stars. We believe that planetary systems all form in a nice disk, and we see a ring of dust around Fomalhaut that in which planets could be forming, or this could be far enough out that this could be a ring that might be similar to, say, the Kuiper Belt in our own solar system.
This is an image. I believe this one was taken with the Advanced Camera for Surveys High Resolution.
Yeah, this
channel.
is the HRC.
We observed it more recently with the
we've
Space
since
Telescope imaging
visited it
spectrograph,
again
and in fact,
2011.
yeah, and in fact, it continues along this orbit that's been predicted here. So there's a longer baseline available now too.
Right, we got 2010 and 2012 images.
Yeah.
And the cool thing about those are that it's not on this nice orbit inside the ring. It actually extends. It's on a very elliptical orbit.
Right, which is even more confusing and interesting.
Which is why I went for this image, because it's easier to understand.
Yeah.
Okay, Mario, you want to share one with us?
Sure, why not? Maybe let's put the bullet cluster, which is the third from the top here.
Yeah.
Yeah, that's a good one.
So, no, it's not this one.
It's a hard chip.
This one, yes. So this actually shows the incredible synergy that you can have between two great space telescopes. This is a combination of Hubble with the Chandra X-ray Observatory. What we're seeing here are two clusters of galaxies colliding, and clusters of galaxies have in them gas, normal gas, lots of hot gas, and that's what described here by the color red. But they also, we think, have around them dark matter. Dark matter is matter that doesn't shine any light, and we know it's there only because of its gravity. In fact, 23% of the density of the universe is in the form, we think, of dark matter. Now, this image is pretty amazing because dark matter interacts very weakly with anything else. I mean, basically, dark matter particles pass through one another without feeling each other, and that's what you see here in the blue. While the hot gas, the normal gas, when it collides, it really collides, and it forms a bow shock, which you can see on the right-hand side. You see the shock that forms, like just when a boat goes through water or when a supersonic jet goes through air. You see that shock front that forms from the collision of the gas. So you see here a separation between the dark matter, which really passed through without feeling at all one the other, and the hot regular gas that shocked and formed this thing. So this, I believe, was actually the very first image that showed this kind of separation and really what we expected from dark matter. As I said, other than dark energy, which is something else, dark matter is the second most abundant form of energy in the universe, and we have seen here, how it is different from ordinary matter.
So, Mario, I think it's worth mentioning that the red that you see there is the actual Chandra image. Yes. Of that hot gas in the cluster.
That's right.
And then the blue is a representation of the dark matter, not the actual observation of the dark matter, but the representation of the dark matter derived from
gravitational lensing.
From the gravitational lensing that's seen within the Hubble image.
That's right. The dark matter you cannot actually see, but you see its gravitational effect through a gravitational lensing, and therefore you can map it. We can map its location, and that's what the blue region here shows.
Yeah, that's beautiful image.
Yeah, thanks for the clarification. Now, that I wasn't wanting to get to that because I know that you can't actually see the dark matter in any way. So the way they just look at the individual galaxy, or the ones that have been lensed by the dark matter and mark it as being dark due to dark matter. Carol, you have something you want to share with us? Any images?
So in the dots theme, so I have two images to show. One is a ground-based image of what's called a globular cluster, which is slide number 6 in my slide. So maybe if somebody can put that up, we're going to just show that briefly, and then
that's a lot of dots.
So it has lots of dots. Okay, so that's a ground-based image of something called a globular cluster, and its particular name is 47 Tucani because it's in Tucani, the constellation. Now, the Hubble image is the next image, and what's remarkable about it is it's only a tiny portion of this cluster that's being studied because the cluster is very big, and we can only see portions of it with the Hubble. Why are these objects important? Well, we've been talking about galaxies and lenses and galaxies far out in the universe, but these clusters are near us. They're in our galaxy, and they are the remnants. They are the old population that formed at the beginning of the formation of our galaxy. And so the stars you're looking at are extremely old. And so we study these clusters, which most of my colleagues think they're really boring, but I like clusters. But every one of those dots is a star, and that's only a small portion of the whole cluster. But we study these to understand how do these clusters form, and then what happens to them over the lifetime of the universe. What happens to the star? And so I love these images of clusters because they're nearby and they do tell an old story, and we need to understand these old with the James Webb Telescope, which are forming when these clusters formed.
That's amazing. That is a great image. Okay, guys. Well, we are nearing our time here on what we think are some of the more amazing images by Hubble. We could do this all day. You wouldn't believe how many images we had.
So much more to put up.
I know.
Tony.
Yeah. Oh, sorry, Ken. Go ahead.
We put up all these dots. Could we put up a few squiggly lines?
Yes. We need Ken's image. Yeah, we need Ken's data.
I need 1 minute.
Yes, absolutely. By all means, put it up. We should mention while it's being put up, though, that there are more than just cameras on the Hubble, right? You want to talk about that? I mean, first of all, we have how many cameras and what other instruments are on Hubble right now that are taking data?
We have the advanced camera for surveys and the wide field camera 3, which are the two primary cameras. Mm-hmm. Then we have the Space Telescope imaging spectrograph, which can take pictures but also takes spectra, and the cosmic origin spectrograph.
Okay, so and so when we say we don't want to limit you just to visual images, if you think that some of the spectra from Hubble is also some of the most amazing or greatest images taken, by all means, you're feel free to elect those as well. A spectrum is a beautiful thing.
Yeah, I agree. And this one in particular really floats my boat because it shows the presence of oxygen far, far away from galaxies. In the intergalactic medium. So what you're looking at here is light that's been passed through a good chunk of the universe on its way to Hubble, and when it enters Hubble, instead of taking a picture of that light, Hubble diverts the light to a spectrograph, which is an instrument that breaks light into its component colors. So you see the colors here as a function of wavelength. You see the intensity of the light here as a function of wavelength. In this case, it's a very ultraviolet light, and each of those little dips in that overall spectrum that you see there is the signature of different elements in the gas that the light has passed through. The intervening material leaves its imprint on the light from those distant objects, and in this particular case, the imprint is in the form of highly ionized oxygen lines. And those highly ionized oxygen lines are tracers of the gas that eventually form galaxies. And so that's one of the things that I like. And if you look out at how much of you can do all kinds of things with spectra like this, including estimating how much gas is out there. And if you estimate the amount of oxygen that you see out there, and you convert that into mass, you realize that there's as much mass just associated with these oxygen systems as there is in galaxies as a whole. So there's a lot of material out there.
Well, anyway. I don't understand. There's as much oxygen by as there is other stuff
There's
in galaxies?
There's as much hydrogen associated with that oxygen as there is mass in galaxies, right? So most of the mass in galaxies is in the form of hydrogen, and you're using the oxygen here as a tracer, a proxy for that hydrogen, because you can't observe the hydrogen directly associated with that very hot gas. But if you do the conversion, you find that there's as much hydrogen there in all of that gas that's forming galaxies as there is in the galaxies that you can actually see in Hubble images, for example.
Oh, that's amazing. All right.
We could do a whole hangout on spectra, and I would recommend that we do at some point.
I think we should. Yes, we spend an awful lot of time talking about the optical or two-dimensional pictures, but there's a lot to be gained from spectra as well. So I think we should. I like that idea.
I mean, Hubble spends about half of its time taking spectra.
Let me add one thing. You see, there is all this gas that is between galaxies. We call this all this cosmic web. But you cannot really see that because there is no light coming from that. So what you do is you use some very distant source point of light, and you get that light to pass through all this cosmic web, and on its way it's being absorbed by this gas. And that's what you see in these spectra. So these spectra really tell you the structure of this cosmic web that fills the entire space.
Yeah, they're one-dimensional maps, these probes along this one sight line through the universe. And through lots of various probes and through other theoretical studies, we've built up an idea of structure of the universe. And it's amazing just how much we can learn about the three-dimensional structure of the universe from these very one-dimensional sight lines through it.
Awesome. Well, there you go, guys. I want to see now. I want you guys to start showing me some spectra also in your submissions. So I think there's a lot to be getting. Well, I think it's important. I mean, Alberto, Scott, this has been really great. I mean, this has been a lot of this was one hangout I was very much looking forward to, and I'm really glad we got a chance to do this. You guys have any thoughts?
I'm going to put up even more of the ones that we didn't actually get to share. There's so many more that we had set aside for this hangout that we haven't even got to. So I'm going to keep putting them up on the event page, and I really hope that the audience out there, either on YouTube, Facebook, Twitter, Google+, find your images and let us know what you love and why you love it. More importantly, why.
Yes, that's very
important.
Tell
us how it's inspired you since 1990, almost 25 years. On wanting to understand the universe and how I find looking out through Hubble and seeing these images really helps me find humanity inside those, and so we can actually see where we've come from, what we have in common with the rest of this expansive universe.
There's nothing I can add to that.
I know. Follow that, Alberto.
There you go, Alberto.
Really?
Your move.
Yeah.
I can. I'm just saying that this should probably be part 1 of 99 because, I was looking at all the images that we have. I wanted to talk about, Hubble has looked at planets in our solar system. We had a close encounter with a comet in 94, I think, Shoemaker-Levy. We saw it smashing on Jupiter. So there's incredible things that we've done from the very, very close by, from our solar system all the way to the early universe, which is probably the most remarkable legacy that Hubble will leave us.
That's right, and I would argue that the Hubble Space Telescope is probably the most important scientific instrument built by humanity, and I include the LHC in that statement. I'd love to see, yes, CERN is doing a lot of great work, but I still would put Hubble up against it any day. I'd love to see smackdown on that. That's right.
And the data is all yours.
That is true. Which is
excellent point. Excellent point, Carol. That's right. Excellent point. Excellent point. That it is available for you to get all the time. In fact, we're going to talk about that a little bit tomorrow on our Comet Ison hangout, where you can get Hubble data yourselves. So, guys, thank you to all of you for participating. This was a lot of fun. I hope Hubble huggers, you guys get out there. And do you have something you want to say, Carol?
No, I'm giving the Queen's wave.
That's so, yes. That's, yes. Thank you to all the little people out there. Okay, Ken, Frank, Mario, Frank, and Carol, thank you and Zolt, sorry, you're on the wrong side of my screen there. Thank you all very much for for participating, taking time out of your day to talk to us about Hubble pictures.
Let's do it again real soon.
Yeah, I think you and I are.
Oh yeah.
Yeah, so we'll see you tomorrow probably.
Yep.
Scott, Alberto, this has been great. Thank you both very much.
Thank you.
Let me remind everybody that the way to interact and let us know what you think is to post on this event page. Use the hashtag Hubble Top Shots to get our attention on Twitter and Facebook. Also go to the Hubble Space Telescope community, start posting in there, and just you can even email us at well, we don't have an email address, I guess, for this, so I guess never mind. But
you can tweet us.
Intertweet us, right. So anyway, I hope you guys will participate. We're looking forward to compiling this list. We will post it. I think we're going to stop taking submissions on it's early next week. I should have probably had that date.
I thought it was the 18th, but I can't remember.
Yeah, the 18th. That sounds about right. So you have until then to give us your submissions. Looking forward to seeing what you guys come up with. Thank you guys for watching, and as always, keep looking up.
Bye, everyone.
I've been with Hubble for many, many years, almost since launch, and I like every minute of it, and I'm sure I'll continue to like it, and hopefully also with the James Webb Space Telescope.
All right, awesome. Thank you, Mario. And I am also very pleased that Dr. Ken Sembach could be with us today. Ken is like the Hubble guy at the Institute. Ken, why don't you introduce yourself?
Hi, Tony. I'm the Hubble guy at the Institute.
Well, that was simple. Glad you could make it. Moving on.
This is the humble Hubble guy.
The humble Hubble guy, yeah.
Yeah. So Tony, my day job is to basically watch out over all things Hubble here. I'm the head of the Hubble mission office here at the Space Telescope. And I have the privilege of working with many, many wonderful people here and at the Goddard Space Flight Center every day to keep Hubble operating efficiently and producing all that great science it produces. I'm trained as an astronomer, so it's a particularly satisfying job.
Awesome. Thank you. And like I said, welcome. I'm really glad you're able to make it. And skipping over Scott and me, who we already have introduced ourselves, with me is Zolt LeVay. He also is the Hubble Heritage Team Lead, and he's one of the guys that are sort of responsible for giving us some of the most beautiful images Hubble has ever created. Hi, Zolt. Welcome.
Hi, Tony. Hi, everybody. Yeah, what more can I say? I've had the privilege of putting together a lot of these Hubble pictures from the data. So we take the data out of the archive and put the images together and make them available to everybody.
So in some way, we are really showing your work today.
In addition to Skywatch, which we're looking to move to mobile media and the internet, I'm actually the Hubble Space Telescope outreach scientist, which actually to me is one of the best jobs in astronomy. It means that they pay me to read all of the research literature, which many astronomers, they have to carve out some time of their day to do that, but I get to do that as part of my job. So I get to see all the different research that's being done, and then I also support the news and the education products that are derived from those discoveries. So scientists are using the Hubble Space Telescope, making new discoveries, and then we roll that into news and education, and so I help do that. And it's like a great job. And the thing that's near and dear to my heart is citizen science, so that's the kind of science where we invite you to participate in our research by helping us find new galaxies, identify star clusters, maybe look for star formation bubbles in the Milky Way. All of those things are possible for you to participate in, and I'm pursuing some of those projects with my colleagues.
Oh, I know just how you feel about having the greatest job in the world. It's like sometimes I can't believe that I get paid to deal with the Hubble Space Telescope every single day. So I know just what you mean. I think we're going to be doing a hangout at some point in the future on some of those citizen science things too that you talked about.
I hope so. Yes.
Yeah. Okay. So crammed all together in one room, we have three astronomers who are extremely in my opinion, awesome guys. So with us, Dr. Frank Summers. Hi, Frank.
Hey, Tony. How's it going?
Also with me is Scott Lewis from KnowTheCosmos.com. Hi, Scott.
Hey, Tony. How's it going?
Hey, Scotty. Hey, can I call you that? Can I call you Scotty?
You could for like once.
Oh, no, come on. No, I'm going to call you Scotty now. And then maybe in tomorrow's Hangout we'll give you a tagline, because for me it's like I stole Keep Looking Up from Jack Horkheimer, and of course Alberto's is Get Her Done. So we got to have one for you too.
Boy.
Yeah.
See, yeah, now we're going to have the YouTube commenters start calling me Scotty when I do Space
Scotty! Yes, you being
Hey.
Okay. All right. Well, welcome, Scott. It's good to see you again.
Yeah, you too.
Let me talk a little bit about before I introduce our other astronomers. I would like to get sort of to the point of what we're doing here. What are we doing and why? And we're kind of doing a social experiment this time around, where at the Institute we are compiling a list of the greatest images ever taken by the Hubble Space Telescope. And to do that, we want to get you involved and to get you help, your help. So to get our brains kind of kick-started into thinking about what images there are and what do we mean by the greatest images, let me introduce some of the people with me now. And we have these guys, to me, are all rock stars. I mean, I have heard about them long before I ever met them, and I'm just really thrilled to have them with me on this Hangout today. Let me start with Carol. I'm just going to go from left to right. So with me is Dr. Carol Christian. Hi, Carol.
Hello. How are you?
Well, I'm good, thanks. And now you were famous long before I met you, because for many years you did the radio show on NPR Skywatch, and so I knew about you way before I met you. It's a pleasure to finally be in a Hangout with you, though. So tell us a little bit about yourself. What do you do all? Hello, Hubble huggers, and welcome to another Hubble Hangout, to our latest humble Hubble Hangout. Our hearty and happy Hubble. Okay, I'll stop.
Wow, the alliteration is strong in this one.
Well, it's easy with H's. It's easy to alliterate with H's. So anyway, so I guess of all the Hubble Hangouts I've done so far, I'm particularly excited about this one, because the topic of this one is about something very near and dear to my heart. It is not an exaggeration to say that images from the Hubble Space Telescope have literally changed my life. And I don't mean that as a figure of speech. I could go on. That could be the subject of its own Hangout, actually. But the images that the Hubble Space Telescope have taken have profoundly affected me, and have ultimately led me here with this great group of people that I'm about to introduce to you to talk about the Hubble Space Telescope and the images from it. So let me get started by introducing my co-hosts, or cohorts, or cohabitant. No, we don't live together, but with me is one of my co-hosts, Alberto Conti. Alberto.
Hi, Tony. How are you?
Welcome. Yes, he is the JWST innovation scientist. And Alberto, real quick, I know this is about Hubble, but I got to ask real quick, how are things going with JWST? We still on track?
Everything's still on track. We have a new instrument just delivered to Goddard a few days ago, and one is going into the cryo chamber for testing. So we're really doing well.
Awesome. So we're still launching in 2018 then. Nobody's dropped a primary or sneezed on the secondary or anything. Good.
Not yet. No.
Awesome.
We won't.
Okay.
Not because they wear masks, right?
Yeah, that's right. They have those sneeze guards and everything. Okay, cool. All right.
On today.
Really good. So you are?
I am an outreach astrophysicist, outreach astronomer in the Office of Public Outreach here at Space Telescope Science Institute. So I also get to talk about the amazing things that Hubble does, working on the press releases, working on educational projects, giving teacher training talks, working with planetariums and museums, working on the website, doing all sorts of cool stuff. But as you know, my favorite thing to do is scientific visualization. I was the scientific visualization supervisor on IMAX Hubble 3D, and together with Zolt Levay, who you'll introduce in just a bit, we have a group here, the Visualization 3D team, that we take Hubble images, we visualize, we create three-dimensional models of them, fly cameras through them, and are able to explain the universe through 3D visualizations. That's what I like to do best.
Awesome. And then right next to him is Dr. Mario Livio. Hi, Mario.
Hi.
Go ahead.
Yeah, well, I'm an astrophysicist. I'm a theoretical astrophysicist, which means I hardly know from which side of the telescope one looks, but I look at what those astronomers are coming down with, and I'm trying to explain all of that and explain the universe. In my spare time, I write a blog called The Curious Mind, which hopefully everybody reads. And in my non-existent spare time, I try to write popular science books, the latest of which is called Brilliant Blunders, where I try to explain all kinds of complex scientific issues in a layperson's language to make science more accessible to a larger group of people.